Welcome back. Before we begin, let's take a look at the roadmap for this section of the course. This section and many of the ones that will follow will be structured similarly. Just like with the AR model, we'll start by examining the mathematical representation of the model. We'll discuss each new notation, learn how to interpret it, and then digest the different parts. Afterwards, we'll start coding. First, we'll highlight which new packages we'll rely on and import them unless we've done it already. Next, we'll fit some simple version of said model to returns and analyze how well it predicts future values. We'll comment on the significance of the coefficients and the log likelihood. And then we'll extract and analyze the residuals. Once we're done, we'll try and find the appropriate number of lags we wish to include for this type of model. Of course, once again, we'll follow the steps from section 6 to determine the best possible predictor. Earlier we mentioned the AR models usually perform poorly when predicting non-stationary processes. To test if this also holds true for other types of models, we'll check how well they predict prices. Be wary that this might cause some methods to fail, so we need to proceed with caution. Now that we've set the tone for this entire section, let's start examining the moving average model. All right, let's get going. We'll be dealing with returns in the initial part of this section. So let's suppose that R is some time series variable. Then a simple MA model would look something like this. R in period t equals some constant c plus a numeric coefficient theta 1 times epsilon in period t minus 1 plus epsilon in period t. Just in case, let's go over the different parts of this equation to make sure you understand the idea thoroughly. For starters, RT represents the values of R in the current period. Next, theta 1 is a numeric coefficient for the value associated with the first lag. We prefer not to use phi, like in the AR model, to avoid confusion. Then comes epsilon t and epsilon t minus 1, which represents the residuals for the current and the past period, respectively. How do we generate these residuals? It's quite simple. We start from the beginning of the dataset and try to predict each value. Depending on how far off we are each time, we get a residual. Therefore, we generate these residuals as we go through the set and create the epsilon variable as we move through time. You can notice some parallels between the AR and MA models. In fact, we can say a simple MA model is equivalent to an infinite AR model with certain restrictions. Not to mention that an inverse relationship exists as well. You can find more details on that in the additional materials to this lecture. Now, in both models, we have the present-day value equal a sum of a constant, some error term, and a lagged value multiplied by an assigned coefficient. The only major difference is that the AR model uses the value of the variable, while the MA model relies on the residual. Finally, there's one more common trait of the AR and MA models. The restriction remains that the absolute value of each coefficient should be less than 1. Once again, this is to prevent compounded effects exploding in magnitude, as we've discussed in the last section. Okay. Apart from sharing a lot of similarities, the two types of models also have several key differences. One such distinction between them comes in the form of determining the maximum amount of lags we are willing to include in our model. While with the autoregressive model we relied on the PACF, with moving averages we rely on the ACF. The reason is, the MA models aren't based on past period returns. Therefore, determining which lagged values have a significant direct effect on the present-day ones is not relevant. Anyways, the total accumulated effects accommodate for these unexpected shocks. Hence, the ACF plot provides us with information on how many lags our model should use. So, to get an idea of how many lags we expect our model to include, we must compute the ACF for price returns once again. In case it slipped your mind, we simply use the plot ACF method from the Stats Models Graphics TSA Plots package. Please take some time to get familiar with the ACF plot. In the next lecture, we'll create our first moving average model. Thanks for watching. Welcome back. In this lecture, we're going to see how to fit a time series into a simple moving average model. You're already proficient doing this for AR models, so this shouldn't be too difficult. Furthermore, we computed the ACF for returns, so we already have a good idea of how many lags we're likely to look at, 8. So let's get coding. Once again, we're mainly going to rely on the ARMA method from the Stats Models TSA ARIMA model package, so we don't have to import anything new. Now, if you open a new notebook, you once again have to go through all the pre-processing parts of the code. If that's the case, we suggest using the template file we've attached to this lesson. The only correction you should make is to remove the line of code where we deleted the first row of the data frame. We did that earlier since we wanted to avoid missing values in the returns column. However, losing data is a practice we should avoid whenever we can. That's why, in just a bit, we're going to adopt a new approach to handle the empty value in the first row. Okay. So we start by defining the name of the variable we'll be using to store the specifications of our model. We already established a neat system for naming such variables, so we write model ret ma1 followed by =. Then, just as we did earlier, we call the ARMA method and set the arguments accordingly. The first one remains df returns, since it represents the dataset we want to model. However, to avoid taking the first row, we add bracket 1 colon bracket after df returns. This notation will use all the values of the return column after the first one all the way to the end of the data frame. This way, we simultaneously keep the entirety of our data frame while handling the no missing values requirements for the method. Unlike the AR model, here, to indicate we'll be taking advantage of a moving average model, we must alter the order values. Let's see how to do that. The first value in the pair order refers to AR components, while the second to MA ones. Since our model contains none of the AR components and one of the MA components, we set the ordered pair 0, 1 as the values for the order argument. Next, we fit the model and summarize the results, using the fit and summary methods respectively. You can notice that the coefficient for the one lag ago, residual, is significant at the 10% level, but not at the 5% level. This shouldn't come as a surprise, since the first coefficient of the ACF was also not significantly different from 0. However, all other coefficients up to 6 lags ago fell outside the blue area, which suggests significance. In addition, the 8th and the 18th lag were also significant, as were some others more than 20 periods ago. Since we expect the compound effects to decrease the further back in time we go, we can disregard the 18th lag and all significant periods that follow it. That's because we expect their impact on today's returns to be minimal. Moreover, we should also check whether we should add the 8th lag as a worthwhile significance, or we should select one of the simpler models. Okay, and that's how you create a simple MA model. It's time to move on to the more complicated and exciting ones. Thanks for watching. Welcome back. In this lecture, we're going to fit a higher lag MA model. We already completed the same course of action for the autoregressive models, so this time it should feel very intuitive. We're going to continue where we left off and fit an MA model of order 2. Then we'll analyze its coefficients and log likelihood and repeat the same process several times over until we fit the one which characterizes the data best. Let's get started. Begin by taking the code for the MA1 model and copying it into a new cell. Then change the values for the order argument from 01 to 02. Once again, this will indicate to the computer that we wish to see how an MA2 model performs. Just make sure you change the names of the model and results variables to reflect the higher order, which goes from 1 to 2. Finally, we want to print out summary results, as well as the outcome of the log likelihood test. Now, this next part is Jupyter specific, but we need to print the summary table and the p-value from the test. If we try to call the LLR test in the same cell without using the print command, we'll only get the outcome of the test. That's because Jupyter only displays the last called variable, function, or method. Thus, we either put the LLR test in a separate cell or just print out the table along with the test result. In this course, we favor the latter because we can get all the results in a single output. Thus, this is the approach we're sticking with. All right, let's examine the summary table. What we notice is that the p-value for the error term 2 periods ago is significant. Of course, this matches our expectations from the ACF plot. However, you can see the p-value for the 1 period ago residual is now also significant. So, we went from having no significant coefficients to having all coefficients significant. This is exactly what we were aiming for when fitting the more complex model. Since one model has significant coefficients and the other does not, we can confidently assume that the MA2 model is a better fit. Nevertheless, directly assuming such statements is problematic in analysis, so we still must run the LLR test function we defined in the previous section. The output is a p-value of 0, which means the MA2 makes significantly better predictions. Fantastic. Before we move forward, we can call the LLR test in the same cell we fit the model. As we saw in the previous section, we do this for the sake of convenience when we must fit several models in a row. That's all done. So let's see how an MA3 model performs. For starters, we make the necessary changes to the code and fit the data. The new coefficient has a p-value of 0, which makes it significant. The same can also be said about the second lag, but not the first. Since the ACF suggests the first period coefficient should not be significant, we can predict that the correct model will have a high p-value for 1 period ago error term. After the summary, we can see the LLR test outcome. Same as the previous instance, we get a 0. This further enforces the idea that the MA3 model is a better approximator than its simpler counterpart. We can continue this process and go through the MA4, MA5, and MA6 models too. Anyhow, their results don't change the pattern. This behavior goes on until we go 7 periods back to the MA7. For practice, it's a good idea to go through all the different moving average models on your own and check if what we are claiming is correct. So, the MA7 model produces a non-significant coefficient and fails the LLR test. Of course, this leads us to believe we're done with our model estimations, right? Well, not exactly. The rules we introduced were more rule of thumb rather than fixed. Experience has led me to believe that we should sometimes deviate from them slightly. However, they are rules for a reason, so don't disregard them completely. That said, to ignore the rules slightly, we need a good reason. Fortunately, we have it here. Do you recall the ACF function for returns we examined earlier? In it, we had the coefficient for the 7th lag be non-significant, but the one for the 8th lag was. Therefore, to be completely thorough, we should bend the general rules of model selection we set earlier and see how an MA8 model fits the dataset. You already know what alterations need to be done to the code, so let's complete them and examine the summary table. Do you notice the coefficients for the 8th lag is significant, while the ones for the 1st and 7th are not? Well, this perfectly matches what the ACF function showed. Moreover, the LLR test suggests that the more complicated model is indeed the better predictor. Now, I assume the last statement isn't unexpected, since the MA7 was not a better predictor than the MA6. So, adding another significant value should surely improve predictions. However, we'd better still test if the MA8 is a better approximator than the simpler MA6. To do so, we must run the LLR test. Conveniently, when we defined a function, we set a parameter df to account for degrees of freedom different from 1. Hence, we should call the LLR test as we've done many times before, but this time add comma df equals 2 in the parenthesis. To elaborate, we set the df argument equal to 2 because we need to estimate the coefficients for 8 variables in the complicated model, which is 2 more than the 6 from the simpler model. We can see that the outcome is 0.027, which is less than 0.05. Therefore, the more complicated model performs better than the simpler one, even though it contains an additional non-significant coefficient. Going back to the ACF plot, we see that none of the next 9 coefficients are significant, so adding any of them shouldn't improve the model sufficiently. Of course, you're encouraged to try these on your own, but as we move forward, we'll focus on examining the residuals of the models that we think fit the data best. Now that we've selected a model based on the ACF and the summarized statistics, we're ready to examine its residuals. Thanks for watching. Hello there. Last time we found 2 moving average models which fit the data well, a simpler one with 6 lags and a more complex one with 8 lags. The LLR test suggested the higher lag model is a better estimator, so let's start by extracting the MA8 residuals. We do so by calling the resid attribute of the fitted model. Since we established a clear naming system for our variables, we know the values should be stored in results, ret, MA8. We want to keep the indexes intact, so we'll simply add a column to the data frame. Of course, we also need to store the results in an appropriate variable. To keep in line with our elaborate naming system, we call it res ret MA8. Fantastic. We have recorded the residuals, and we can observe their mean and variance by calling their associated functions, mean and var. We really prefer easily interpretable answers, so we could round the results to 3 decimals. And we do so by calling the round function and providing the float variable, as well as how many numbers past the decimal point we want to record. To make things clearer, we can print a special message for each one. This way, we'll avoid mixing them up. Just to be on the safe side, we can transform the numeric values into text by calling the string function called str. The results we get are a mean of 0 and a variance of 1.355. Since variance is squared standard deviation, we can use the squared root method from the math library to determine a standard deviation of 1.164. Gaussian white noise implies normality, so we can use the 68, 95, 99.7 rule. This dictates what part of the data is spread within 1, 2, and 3 standard deviations from the mean in either direction. Thus, we expect that most return residuals will be between negative 3.5 and positive 3.5. This means that worst-case scenario, we could be up to 7 percentage points off when predicting the returns for a market index. Of course, this is far from ideal, since 7% can make all the difference when it comes to profits and losses. But before we agree that this model is not great, let's first examine its graph. Please recall from previous lectures how we use the plot method to graph time series with the date index serving as the x-axis. Just as before, we also add a title and set its size. Okay, if we exclude the dot-com and housing price bubbles in the 90s and 2000s and the crisis following them, then the residuals are rather random. They're simply confined with some reasonable range, which can be expected. To test if the residuals resemble a white noise process, we can check for stationarity. Of course, if the data is non-stationary, it can't be considered white noise. Thus, we run the adjusted Dickey-Fuller test. We see that the p-value is 0, so the set is indeed stationary. Even though we got our desired result from the test, stationarity is not the same as white noise, so we should also examine the ACF of the residuals. In case you need a hint, a white noise process produces completely random data, and all the ACF coefficients should not be significantly different from 0. After running the plot ACF method, we can see that most of the coefficients are not significant. In particular, none of the first 17 lags are significant. Of course, the first 8 of them are incorporated into the model, so it's not surprising they are essentially 0. However, the following 9 lags are also insignificant, and this is a testament to how well our model performs. The further back in time we go, the less relevant the values and the errors become. Hence, significant coefficients some 18 lags ago shouldn't play a major role in estimations. This stems from the fact that markets adjust to shocks, so values far in the past lose relevance. Fantastic! For practice, you can analyze the residuals of the simpler MA6 model and comment on the results you obtain. Does it perform better or worse than the MA8? Is there a case to be made for using the former over the latter? Test a few things on your own to arrive at a conclusion which one is better, because picking the correct model is essential for successful time series analysis. Additionally, you can experiment with even greater lags if you wish to. Doing so will show you that the further back we go, the higher the chances of overfitting. That is because the more elements we add, the more we start fitting the model to the data, than vice versa. In the next lecture, we're going to find out how well MA models predict normalized returns. Thanks for watching. Hello again. In this lecture, we're going to quickly examine how the moving average models predict normalized values. This might feel a bit redundant at the moment, but keep in mind that by the end of this course, you'll be comparing different market indexes, so using the normalized values will be crucial. Right. You already know how to normalize a time series, so we'll start from there. We also observed how AR models perform better for returns, so let's normalize them once again. In case you forgot the steps we took, this would be a great moment to pause the video and examine these few lines of code. Okay, after generating the normalized returns, let's plot the ACF of the time series. We see that it is extremely similar to the one we got for the non-normalized values. By observing which points fall outside the blue area, we get an idea of which lags to include. Unsurprisingly, the graph suggests using either an MA6 or an MA8 model yet again. Based on our experience with the AR models, such outcomes are less than shocking. But in order to be completely diligent, it is still best to fit said models and examine their coefficients. Let's start with the MA8. You should be comfortable with all the steps for defining the correct model, fitting it to the data, and printing out the summarized statistics. Just remember to choose appropriate variable names when doing so. Please remember that if you have trouble emulating the code in real time, you can always pause the lesson until you catch up. You will learn best if what you're seeing in the course is replicated in your Python notebook. Now let's examine the coefficients and associated p-values. Do these resemble the ones we got for non-normalized returns? In particular, are these identical to the ones we examined a few lessons back? Once again, we see that normalizing the input data doesn't affect model selection. Of course, we'll have a quick look at the residuals as well to ensure the MA8 is the correct model for this case. Certainly, we first need to store the resid attributes from the results variable. Then, we need to plot it, along with its ACF. We've already completed those steps a few times before, so you should feel comfortable replicating the code on your own. Perfect. The ACF suggests that the data resembles white noise, so our model choice is supposedly correct. For homework, you can try and see how an MA6 model performs when modeling normalized returns. Of course, if the results are strikingly similar, make sure to conduct the LLR test in order to support our claim of choosing the more complex model. Now that we're done fitting moving average models for normalized and non-normalized returns, we're ready to test how they perform using non-stationary data. Thanks for watching. Welcome back. In this lecture, we're going to examine how moving average models perform when modeling prices. We already determined that autoregressive models are less reliable when estimating non-stationary data compared to stationary data. So it's time to see if the same goes for the MA models. For starters, let's once again examine the ACF to get a rough idea of how many lags we expect to include in this model. Just call the plot ACF model on the market value column of the data frame and observe. Sadly, the coefficients for all 40 lags seem to be significant. This suggests that any higher lag model would be preferred to any lower lag one. This leads us to believe that we'd have to use an infinite MA model to fit this data. Since no such thing exists, it seems that no moving average model would be a good estimator of prices. But before we completely discredit this result, let's try to fit several MA models for prices and examine their results. Okay, I believe you already feel comfortable typing up the code for this part, since we've already used the ARMA method on numerous occasions. Just try to stay in line with the strategy we set earlier in the course when naming your variables. Now, let's examine the summarized table. We can see that both the constant and the MA1 coefficient are significant. Furthermore, we see that the one lag moving average parameter is equal to 0.9573. This is incredibly close to 1, which means our model tries to keep almost the entire magnitude of the error term from the last period. One way to interpret this is that each time the model tries to predict a value, it actually tries to maximize on the error from the last time. Since this is a simple model with only one lag, the error term contains all the information from the other lags. Therefore, our model has established that this information is truly valuable and tries to use it. Let's look further into it. Our estimate for period t-1 equals some constant c plus some factor theta 1 times epsilon t-2 plus epsilon t-1. Also, our estimate for the period t is some constant c plus some factor theta 1 times epsilon t-1 plus epsilon t. If we substitute epsilon t-1 from the first equation into the second, we get the following. xt equals c plus theta 1 times open parenthesis x t-1 minus c minus theta 1 times epsilon t-2 close parenthesis plus epsilon t. Now, if the parameter coefficient theta 1 is really close to 1, like in our case, then the equation simplifies further. xt equals c plus x t minus 1 minus c minus epsilon t minus 2 plus epsilon t. Obviously, we can get rid of the two constants, which leaves us with xt equals x t minus 1 minus epsilon t minus 2 plus epsilon t. Thus, our model is essentially an autoregressive model, which takes into account the error from 2 terms ago. Of course, if we go further back and we express epsilon t minus 2 in terms of x, we'll see a similar trend. Hence, an MA1 model, where all the coefficients are extremely close to 1, is just an approximation of any ARN model, which only takes the error term from n periods back. Right. Of course, we can use the data and fit an MA2 or an MA3 model just to be sure. However, from the ACF, we can already tell that the magnitude of the coefficients for both periods would be extremely close to 1. You can test this on your own for practice, but we've seen enough to conclude that MA models do not perform well for non-stationary data. But wait, didn't we say that MA models were great in modeling random walks because they take into account our mistakes? Well, in all honesty, the moving average aspect of models does that. However, to actually do a decent job at modeling a non-stationary process, a model should also use the previous period's values as a sort of diving board. And that means some combinations of AR and MA models would be best. Thanks for watching. Welcome back. In this section of the course, we learned from our mistakes and incorporated past period errors into our predictions. This resulted in some correct predictions, but the residuals did not fully resemble white noise. Since we reached this exact same outcome using autoregressive models, it seems like neither type is sufficient to predict price returns. Well, not on its own at least. But what if we could combine the two? We already know that the AR model made good predictions, but failed to adjust quickly to unexpected shocks. What should remedy the situation is accounting for the residual values, since the MA aspects smooth out the predictions. Now we examined the MA models that accounted only for the residuals. These needed a baseline to perform well, so we could use present values to provide that. Thus, if we had a model that takes into account both past values and past errors, then in theory, it should solve the issues each one has individually, since it contains both the AR and the MA aspects. Such a model is known as Autoregressive Moving Average Model, or ARMA for short. Now you know these exist, and this explains why the method we use to define them in Python has the same name. The order argument represented how many lags of each aspect we wish to include. The first value expresses the number of lags back we want to incorporate, while the second expresses the amount of lagged errors we wish to account for. In fact, ARMA models are fantastic because they not only take into consideration the actual results, but also how far off our predictions were. This enables us to calibrate expectations on the go without waiting for the markets to respond naturally. Hence, we can account for shocks more easily when our predictions are significantly off. If it seems like we're rushing through the idea of ARMA models, don't worry. We've dedicated the entire next section to them and how they perform in predicting market returns. We will also provide the mathematical background they're based on and much, much more. But I don't want to spoil the fun, so thank you for watching, and we'll see you in the next section.